Hi guys, welcome to chapter 14. We're going to start talking about energy in this chapter. Okay, so what is energy? It's one of those weird scientific things. It's a little difficult to describe or even give a definition to, but it is the ability to do work. That's the best thing. That's the closest thing to a definition we have. Remember, work is applying a force to an object, and the object moves in the same direction as the force. So, energy is the ability to do that. Energy is what kind of allows us to exert that force to an object. Okay. Now it gets a lot more complicated than that, and energy is this kind of crazy thing in the universe. It actually is what holds all matter together. Without energy, there would be no matter. Okay, and so in later chapters, we're going to talk a lot about the particles of matter, and we're going to talk about how they move and the vibration of those little particles. That's all examples of energy. Okay, so Einstein came up with this word that he talked about the kind of interrelationship between matter and energy. He said they're convertible. Basically, they're different forms of the same thing, and that's a basic explanation of his famous equation E equals mc squared, where E is energy and m is the mass of some type of matter. We've talked about the law of conservation of energy and the law of conservation of mass, and this is how they kind of go together. Okay, so again, speaking of the law of conservation of energy, that's just this concept that energy doesn't get lost. If you have a closed system, okay, so everything can be accounted for and contained, the total energy is always the same. So we kind of talk about the universe as a closed system, and the energy is always the same. It's just it's constantly being transformed into one form or the other. Okay. And simply put, the law of conservation of energy just tells us that energy cannot be created or destroyed. So you can't get energy out of nothing magically. We're always looking for efficient ways to get energy, but it has to come from something. But it's also not lost. You might, objects will stop because of things like gravity and friction and Newton's first law of motion and things like that. But it doesn't mean the energy is gone. It's just been transferred into something else. Okay. All right. So we're going to talk about both kinetic and potential energy. Let's talk about kinetic energy first. Basically, kinetic energy is the energy of motion. Any object that's moving has kinetic energy to it. Okay. Got a baseball here. I move the baseball. I toss it around. Okay. It's demonstrating kinetic energy. I sit it on the counter here. It's not moving at all. Okay. It does not have kinetic energy. The amount of kinetic energy something has, and it can be calculated. We'll talk about that formula in just a second. The amount of kinetic energy an object has is very similar to momentum. Okay. It depends on the mass of the object, and it depends on how fast the object's going. Okay. If I kind of roll this into you, it's not going to really hurt. But if I throw this really fast, it's going to hurt because it's going to be moving faster. So it's going to have more kinetic energy. Same thing with a really, really large object. Okay. It doesn't really matter how fast it's moving. If a really, really heavy object hits you, it's going to carry a lot of kinetic energy. If a car bumps into you in the parking lot, it's going to move you. It might not hurt you, but because there's enough kinetic energy, it will move you. Okay. Energy, because kinetic energy and any energy is measured in joules. I'll get to that last statement in just a second. Let's look at this formula now for a second. Here we go, my red pen. Okay, so we will be calculating this. Okay, the kinetic energy is, again, it's due to the mass and the speed. So we take the mass times the velocity, we square the velocity, multiply it by the mass, and then multiply that whole thing by half or divide it by 2. And that's what gives us the kinetic energy. Okay. We're going to do a couple of those equations in just a minute. This is what takes us to potential energy. If something is stationary, it does not have kinetic energy. Okay. So if I put this on the counter, you can't see it. There it is right there. It does not have kinetic energy. It does not move. Okay. However, that doesn't mean all stationary objects don't have energy. This baseball does not have kinetic energy right now, but it still has energy, and that's potential energy. We'll get there. Okay. Let's do a calculation first. So because of this idea of size and mass and heavier objects tend to have more kinetic energy. What would you rather be hit with, a train or a feather? So that question is posed on page 327 in your book, and you can use the formula there to calculate both. It says a slow moving locomotive has a mass of 107,000 kilograms, okay? And it's moving at 0.25 meters per second. Okay? How much kinetic energy does it have? All right. Well, I have to square that first. This is the velocity. So that gets squared, and then it gets multiplied by that, and then all of that gets divided by 2, according to our formula. Okay. So 0.25 squared times 107. This is riveting video, isn't it? Divided by 2. Very good. That gives me 3.8 joules. Okay. The book rounds it up to 33, or rounds it down to 3340 joules, but I'm going to be more precise. Okay. Now, the second example is the feather. On average, the mass of a chicken feather is, wow, it's really small, 0.00000, there's a decimal there, 820 kilograms, really tiny. The speed of the fastest ever man-made object is 98,900 meters per second. So if we could get that feather to move at that velocity, 98,900 meters per second. We're going to square that, multiply it by that, divide it by 2, okay? Now, I'm not going to calculate that one out. It's too many zeros. I don't want to take any more time. When you calculate that all out and round, that comes out to be 40,100 joules. So this feather would have way more kinetic energy than that locomotive right there, simply because it's moving so fast. It's a total made-up scenario. Probably can't get a feather to move that fast, but you get the point. Okay, so now let's talk about this baseball that I'm just holding in my hand. Okay, it has potential energy, which is known as stored energy. It could be used later. And the main kind of potential energy that we talk about is gravitational potential energy. So something has the potential to fall, okay? I don't have to pick this up. I don't have to put any more energy into this ball to get it to move. I don't have to hit it. I don't have to blow on it. I don't have to pick it up. I don't have to do anything. All I need to do is turn my hand and the ball is going to fall. That means there's energy stored in it that allows it to move, okay? Gravity's pulling it down. Once it starts moving again, guess what? It's kinetic energy, okay? So this object is hanging up there. It's not moving at all. So there's no kinetic energy, but it has the potential to move. It's stored inside of it, okay? As soon as that's cut, it drops. It's moving again. It's kinetic energy. Now, when it's on the ground, so if this object is on the ground right here, okay, it doesn't matter. There's no energy. There's no kinetic. There's no potential. It doesn't have the potential to move anymore. You have to put energy into it or force into it to get it to move at that point, okay? The formula for gravitational potential energy is much easier. It's just the mass of the object times the acceleration due to gravity, which is a constant. That's at 9.8 meters per second squared. And then the height of the object, okay? And so since this is just straight multiplication, we're just multiplying these numbers together, you can see that the higher that number goes, the higher this number is going to go. The higher an object is, I could drop this on my hand and it's not going to do much. If I dropped this off of a building onto my hand, it would, hurt a lot worse. It might break a bone, okay? So the higher objects fall from, the more potential energy they have stored, the faster they're going to fall and then demonstrate more kinetic energy, okay? There's two other types of potential energy that we'll talk about though. One is elastic potential energy. Things that are stretchy or springs have elastic potential energy, okay? So when I pull this rubber band, all I need to do, it's got the energy stored in it right now. I don't need to do anything else but let go and it shoots, okay? Now, that rubber band actually demonstrated two kinds of potential energy. Because I was holding it up, it had gravitational potential energy. Because I stretched it, it also had elastic potential energy. And the third type is chemical potential energy. The food you eat has energy stored in its chemical bonds, and the act of digestion breaks those bonds apart and it releases energy into our bodies. That's how our bodies get energy. So there's a lot of stored potential energy in the chemical bonds and all these different reactions. Remember we talked about chemical reactions? Reactions either absorb energy or release energy. Well, that's the energy. It's that chemical potential energy. Okay, so look at page, and this is the simpler formula. This is page 329. It says, how much gravitational potential energy does a 0.25 kilogram apple on a tree have if it is 3 meters above the ground? Okay, and we know that acceleration due to gravity is 9.8 meters per second squared. So we just multiply all three of those together. So 0.25 times 3 times 9.8, and that's going to give us, this is rounding again, 7.4 joules of energy. You don't have to worry about squaring anything, you just multiply it, okay? But you can see what would happen. If then I put that up to 6 meters, that's going to go up quite a bit higher. Okay, let's see how much higher. So 0.25 times 6 times 9.8. Look at that. You math people already had that. It just about doubles it. Since I doubled the height, I double the overall potential energy, the gravitational potential energy. All right, that's it for section A. Bye-bye.